Number 78 should be D, as in dog, 78. And number 82 should 82 be something else? I think it should be C. I think. I could be wrong. Let's see. Let's see what I changed it to. Where'd it go? Open. Key. 82 should be C. 78D, 82C. Okay? Are there any questions other than those ones, which were obviously wrong? Start with. Yes. Sorry? 14? 114. Okay, yeah. Okay. $114. So we want to know the solubility of aluminum hydroxide, so AlOH3 in 0.0182 molar KOH. So we can write a KSP expression for this. And this is a very low solubility compound. You can see that the KSP is times 10 to the negative 33. What does that mean about the ion concentrations, aluminum hydroxide, that are coming from aluminum hydroxide? They're really small. Therefore, the concentration of OH minus can be taken to be 0.0182 because it'll be plus 3x, but x is going to be teeny, teeny, tiny. Yes? Yeah, so we can say plus 3x, but this is going to be insignificant. Okay, so we can say, okay, well, I could find out then the concentration of aluminum. Yes? And because this is 1 to 1, if I know the concentration of aluminum, I know the concentration of aluminum hydroxide. And the solubility of aluminum hydroxide is going to be equal to the concentration of aluminum hydroxide, which is going to be equal to the concentration of aluminum. So if we solve this for aluminum, we get, I'm kind of running out of room here, but that's okay. We get concentration of Al 3 plus is equal to KSP divided by concentration of OH minus cubed, which is equal to 1.9 times 10 to the negative 33 over 0.0182. Now it's actually 0.0182 plus 3x, but the 3x is so small that we can just ignore it. Okay? And we need to cube that. And so we get 1.9 times 10 to the negative 33 divided by 0.0182 cubed equals, and I get 3.15 times 10 to the negative 28. So that would be A. Did that make sense? Cool. Yes? 52. Excellent. Okay, in an experiment, now this trial ion product, that is the trial KSP, yes, which is the same as Q, okay? So we mix equal volumes of 0.0020 molar lead Now, because it's equal volumes, you can make them anything you want to, but you're basically, your dilution factor will be 1/2. Yes? So if you can see that it's just 1/2, you can just go like that. Okay, if you don't see it, you can make it any volume you want. You can say, let's say both of them are 100 milliliters. You can just make that up. Yes? You can be like, okay, 100 milliliters over 200 milliliters. Doesn't matter. So 0.002 divided by 2 is 1 times 10 to the negative 3. And 0.0040 molar I minus times 1/2 is 0.004 times 1 divided by 2 is 2 times 10 to the minus 3. And our KQ, y'all done? Cool. Okay, put that in there so I don't lose it. All right. Now we're dealing with PB and I, so the compound itself is PBI2, right? Because we got 2 plus and 1 negative. And so it's PB2 plus 2 I minus. So our Q then would be lead times iodide squared. So that would be 1 times 10 to the negative 3 times 2 times 10 to the negative 3 squared. So 1e3 negative times 2e3 negative squared equals 4 times 10 to the negative 9. Is the answer key wrong? That could be. Let's take a look. 52 should be A. Yes. Okay. So let's go change that. $52 should be A. There we go. Anything else? Yes. 81. Okay. Hmm. 81. What is the value of silver in a saturated solution of silver chromate at 25 degrees Celsius? So in order to know the silver, we get 2 silvers and 1 chromate. And we will be able to find the concentration of silver chromate, because we're going to call it X. We're going to let the solubility of Ag2CrO4 equal X, which means that silver is 2X and chromate is X. And if you remember, this is a multiple choice, so you don't actually need to write this. Yes? And you can also just say KSP is equal to 4X cubed, right? And our KSP, we can look that up in our table. Let's go look and see what we've got. Silver chromate, 1.1 times 10 to the negative 12. Okay, so we have 1.1 times 10 to the negative 12 is equal to 4x cubed. So x is equal to, I'm just going to write this all down, but you would not show any of this probably. Negative 12 divided by 4, that's x cubed. 1.1 times 10 to the negative 12 divided by 4 is 2.75 times 10 to the negative 13 is x cubed. So x is equal to the cube root of that, 6.5 times 10 to the negative 5. And the concentration of silver is 2 times that much. So we get 1.3 times 10 to the negative 4. Is good? Okay. Yes. 20. And you had another one? 63? 62? Okay. 20 and 62. Okay, number 20. A precipitate of lead chromate is formed by mixing a solution of potassium chromate and lead nitrate. It would be possible to redissolve this precipitate by adding a concentrated solution of, now we need to make sure that we're looking at this. This is the information for question number 20. All right. Would it make sense to add chromate ions? No. Would it make sense to add dichromate ions? If this shifts to the left, now we've made more chromate, and that would cause this to go up, and that would cause that to go that way. So that's not helpful. How about a strong acid? Yes, because if we increase the strong acid, we are increasing the concentration of H+. This shifts to the right, which uses up the chromate, which means this is going down, which means this will shift to the right. So you can redissolve that precipitate using that process. Okay? In fact, if you ever do that lab, there is a lab where we do that, and no, actually not that one in particular, but there is a chromate lab where you get precipitate stuck to the side of the container, and you can get rid of it by adding strong acid. Okay, and we also wanted number 62. Concentration of potassium in 300 milliliters of 0.04 molar K3PO4. Just to let you know, this is moles per liter. So does the concentration depend upon the volume? Will I have a different concentration if I take a different size volume? So if I was to just take a sample of this, that's supposed to be like a pipette bulb, but it's not working very well. So say I just took like a little sample of it, would the concentration be different? No, you can imagine like if it was this dark, right? This would also be the same level of darkness, right? Like it wouldn't depend on how much there was, right? It's the same moles per liter because you're dividing by the liters. So the moral of the story is that you don't need to worry about that 300 milliliters at all. It's just there, right? So you can just say, oh, well, I know that there are 3 potassiums for every K3PO4, so I can take 0.040 and multiply by 3. And we get 0.120. See? Anything else? Yes? No, you can project more than that. I heard you at lunch. 86, excellent. It's so funny because 2 of my quietest students, they're in here at lunch. You're one of them, Aaliyah's the other one. And they both speak loudly when they're in here at lunch, but they don't speak loudly in my classes, but that's okay. All right, let's see what we got. 81. Sorry, did you say 81? 86. Thank you. I'm not paying enough attention. Okay, 86. So which could be used to prepare a solution of S2 minus with a concentration greater than 0.1 molar. Now that 0.1 molar is special because it is the number here. So soluble, if it's soluble, you can prepare 0.1 molar. If it's low solubility, you cannot. Okay, so let's go back here. And so we need zinc, lead, silver, potassium. Oh, look at this, greater than 0.1 molar. That means you need a compound that is soluble, and we all know that all alkali salts are soluble, so it would be that one there. $67. Okay. Okay, we have iron 2 fluoride. We know the concentration of fluoride is 1.68 times 10 to the negative 2 molar. What is the molar solubility? So this is 2 fluorides. So we would take that number and divide by 2, 1.68 times 10 to the negative 2, divide by 2. So that would be 8.4 times 10 to the, oh yeah, this should be a negative 3. Okay, that's a typo. Times 10 to the negative 3, and it should be C. Okay, yeah. Yes. 15, 13. Okay, so we have silver acetate in equilibrium with its ions. So we have AgCH3, COO, solid in equilibrium with Ag plus CH3, COO minus. So you want to take a look at this equilibrium and you want to say what will shift this equilibrium to the right, because that will cause more of it to dissolve. So will we be able to make more dissolve if we add silver nitrate, which gives me silver ions and nitrate ions? If we increase the concentration of silver, which way does the equilibrium shift? To the left. Is that what we wanted? No. Okay. So not this one here. How about nitric acid? We have H plus and we have NO3 minus. Can the H, well, obviously it's not nitrate because nitrate doesn't react with anything. Can the H react with anything there? Ooh. Think about it. What is acetate? Acetate is the conjugate base of a weak acid, so can it accept hydrogen ions? It's a weak base. Can it accept hydrogen ions? Yes. Okay. So you would have H plus CH3 COO minus reacts to give you CH3 COOH, which causes this to decrease, which will cause it to shift to the right. Now, even if you didn't get that, you can do it by process of elimination by saying, if I add acetate, that would increase concentration of acetate, which would shift the equilibrium to the left. And what if we evaporated some water? Will that cause more salt to dissolve? No. So you've eliminated, by process of elimination, even if you didn't know what happened, you're like, well, definitely it's not those three, so it has to be B. Okay? That is number 13. Yeah. Yes. 72. Which of the following has the lowest carbonate? So we have ammonium carbonate. What do you know about ammonium salts? They are soluble. And if you don't know, you can go look it up. You can say, oh, where's ammonium? Ammonium is soluble with all ions, so it's definitely not that one. And then for the other three, if you look on your table, it's magnesium, calcium, and strontium. Where'd they go? With carbonate. Oh, they're all low solubility. So what do you need to look at? You would need to compare their KSP values. So we would look and we would say strontium carbonate is 10 to the negative 10. Calcium carbonate, was it magnesium? What was it? Sorry, was it magnesium? Yeah, okay. Magnesium carbonate is 10 to the negative 6, and calcium carbonate is 10 to the negative 9. So which has the lowest concentration? That will be the one with the smallest KSP, so that's going to be strontium carbonate. Okay. Number 72. Yes. 3. Cool. Given the following data, which precipitate would form first upon dropwise addition? Do you guys know what dropwise addition means? It just means you take it and you add it drop by drop. Add a drop, add a drop, add a drop. So what you would do is you would have your 4 test tubes, and you would add 1 drop to each of them, and you would see what happens. Yes? And then you would add a 2nd drop to each of them and see what happens. And at some point, one of them is going to form a precipitate and the others will not. They will, but you'd have to add more drops. Okay, so let's say it takes 5 drops and this one forms a precipitate, or 2 drops. Let's say this one forms a precipitate at 2 drops. Which one was it? Well, these are all 1-to-1 salts, yes? And which is the least soluble of those salts? AgI is the least soluble of those salts. So what that means is that this is going to be your AgI. You'll need the fewest drops to cause a precipitate to form because there is the least room at this hotel. Yes? The smaller the KSP, the smaller the hotel. Yes? So fewer ions can check in. 103? 100. 100 is missing some units. So these should all say molar. This should say molar. This should say molar. This should say molar. Okay. Hopefully you guys can figure that out. In which would I expect AgCl to have the lowest solubility? I would want the highest concentration of one of these 2 ions. So I have AgCl in equilibrium with Ag plus and Cl minus. This guy has 0.015 molar Cl minus. This one has 0.02 molar Cl minus. This guy has 2 chlorides, which I would have drawn me to it in the first place. So that's going to have 0.04 molar Cl minus, and this has 0.02 molar silver, so that'll have the same effect. So this is going to be the lowest solubility because it has the most ions already checked into the hotel. Did that make sense? Yeah, good stuff. Anything else? Yes. 116? Excellent. All right. What is the solubility of lead chloride in a 0.15 molar solution of HCl? So we want the concentration of PbCl. Cl2. So we know the KSP. And what is this information here telling us? It's telling us that the concentration of HCl is 0.15 molar. What is relevant to this question? Is it the H or is it the Cl? It's the Cl. Now, KSP is 10 to the negative 5. It's not really super small, but it is really small. So is the concentration of chloride from dissolving lead chloride going to be significant compared with 0.15 molar? And the answer is no. Like if you wanted to write it as a rice table, you could say I've got PbCl2, la 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 la, Pb, whoa, what was that? Pb 2 plus 2Cl minus. And you could say, okay, I have initial concentration here is 0. Initial concentration here is 0.15. Some of this dissolves. So you end up with, that's a solid though, so we don't use it, right? X 0.15 plus 2x. However, this is assumed to be insignificant. Yes? So really what we've got is we've got KSP is equal to the concentration of lead times the concentration of chloride squared. And so chloride squared is, let's solve for lead, because that's the one we don't know. KSP over chloride squared, 1.6 times 10 to the minus 5 over 0.15 squared, which is 1.6 times 10 to the minus 5 divided by 0.15 squared is 7.1 times 10 to the minus 4. That's the concentration of lead. Well, what's the ratio between lead and lead chloride? 1 to 1. So this will also be 7.1 times 10 to the minus 4, which can't be what it is, because is there? Yes, there it is. Okay, D. There we go. Yeah. So, you know the maximum and minimum problems? If they ask you for the solubility and you're given the concentration of one of the ions, it's the same as a max-min problem. It's the same as a maximum minimum problem, because if they say, what's the maximum concentration of lead? That's the maximum concentration of lead chloride, which is the solubility. Yeah, so finding the solubility when you already have one of the ions present, it's just like a maximum minimum problem where you have one ion concentration, you have the KSP, solve for the other ion concentration, and that will give you your solubility. Yes, 39. Which of the following would form an ionic solution? How do you know you have an ionic solution? Metal or NH4? Who has a metal or NH4 at the start? That would be C. And that's it. Yeah? Sorry? 40? Yep. So you know what? This number here, 0.01, do you remember why that number is special? It's the one that decides whether things are soluble or not. So let's go find out. Zinc hydroxide is low solubility. So it has to be less than 0.1 molar. How are we doing? 81, sure. We did 81. Oh, okay. I'm like, hang on, what's happening? Yeah. So this is very much like the, this one is, let the solubility. So if you find the solubility, then you will know the concentration of silver because they are related in a 1-to-2 fashion. So you're looking for the solubility. So let the solubility equal X. And that means that our concentration of Ag2CrO4 is X. Silver is going to be 2X. We can go through the whole rigmarole, or we can just, for multiple choice, remember that KSP is equal to 4X cubed. Plug in KSP from the data table. And we solve for X. Let's do the algebra. And remember, X is the concentration of Ag2CrO4. And the concentration of Ag plus, if you recall, was 2X. So that's going to be 1.3 times 10 to the minus 4. How are we doing? Yes. 47. Yep. Yes. Yeah, for sure. You 100% at the office. Okay. Where were we? 47. To determine the solubility of a solute in water, do you want the solution to be saturated, unsaturated, concentrated, or supersaturated? Well, first of all, you might not even know what supersaturated means. So you could just throw that answer out, right? Because if I've not taught it to you at all, then you can just be like, whatever. Supersaturated just means that you've heated the solution and you've added more solute, and then you cool it slowly so crystallization doesn't start. Okay, so you actually end up with more solute dissolved than you normally could by other means. Okay, and usually if you do it like that, it's actually kind of cool. If you just put a seed crystal into it at that point, the whole thing will just go and it will crystallize out. It's pretty neat. Anyway, What the heck does concentrated mean? Just it doesn't have a distinct meaning. Do you know what I mean? So it's not going to be that one. And if we want the solubility, solubility is the max concentration. So we want to have a saturated solution. Yes. 25. Which of the following will increase the solubility of Ag2CrO4? All right, so if we are adding Ki, which of those two ions is important? Is it the K or is it the I? It's going to be the I because K is soluble with everything. Does I react with either the Ag plus or the CrO4? And you can look and see, does I react? Here's iodine. Does it react with silver? Yes, it does. So we go back here and we say, if I was to put in iodide, this would form a precipitate of AgI, solid, which would cause silver ion concentration to decrease, which would cause it to shift to the right, which increases the solubility. How would it silver decrease? You would have silver, which is just hanging around right now. It sees the iodide coming from here, and it says, oh, I like bonding with iodide. So I make AgI solid. So I am using up the Ag. Does that make sense? Yeah? So I have less of it. Now, you could also do it by process of elimination. If you add silver, you're increasing the silver, which would cause it to shift to the left, which would certainly not increase the solubility. Same thing with adding chromate. Chromate would increase the concentration, which would shift it to the left. That would decrease the solubility. And adding more solid does absolutely nothing to the solubility. Okay, so that's doing it by process of elimination. If you eliminate C, B, and D, you're left with only A. Okay? Anything else? Yes? 45? The compound Ag2S has a solubility of 1.3 times 10 to the minus 4 moles per liter. So we have a 2-to-1 compound here. So this is a lovely opportunity to use KSP is equal to 4x cubed, if you're comfortable doing that. If you're not comfortable doing that, you can go and you can say Ag2S in equilibrium with Ag plus, two of them, plus S2 minus, and we have X, and we have X, and we have, 2X and X. And then our KSP is equal to silver squared times sulfide, which is equal to 2X squared times X is equal to 4X squared times X, which is equal to 4X cubed. But we're in the multiple choice, so if you know that, that just saves you a lot of grinding through of all of it. So the solubility is 1.3 times 10 to the negative 4. So that's going to be equal to 4 times 1.3 times 10 to the negative 4 cubed. So that is 2.2 times 10 to the negative 12. Is that an answer? Yes, it is. Huzzah. Yes.
29.
29. Okay. Which of the following solutes could produce at least 0.1 molar? What's special about 0.1 molar? You need to have a salt which is soluble, because of course, if we look at our table, soluble means greater than 0.1 molar. So, where did we go to? We have, so at least means we need it to be soluble. I know that all alkali salts are soluble, so that's going to be my choice. I mean, I could go look at the rest of them, but they will, I know that sulfites are very low solubility with most things. So it's going to be this one because it's got the alkali. How are we doing?
Go over this question because why did
Yeah, page 38, number, that one, that example, yeah. So in our workbook, 3.2c, oh, we're not going to worry about that one. Nope. Why not? Because we're not. Okay? If you want to talk to me about it later, we can. Yeah. Anything else? Yes. Could do. I mean, I don't know. I know that some versions of my test have that on it and some of them don't. Because it's just like a random which version you get. Okay? Anything else? Yes. 82. Okay, I might copy this somewhere else because I've made a mess of this whole thing. Okay, control press. Okay. And you know the answer key to 82 is fixed, right? Yeah, okay. Okay, so over here we go. There we are. So we have equal volumes. Did we not do this? Oh no, that was a different one. Yeah. Okay, so we have equal volumes, and once again, that means that we are halving the concentration, okay? Because if you started with 100 milliliters and they were both 100 milliliters, you would be dividing by 200 milliliters. That would be your final volume. That's VI and that's VF. And so that would be times 1/2. If you started with 350 milliliters, you would finish with 350 plus 350 is 700 milliliters, which is 1/2. So if you're adding equal volumes, you're always going to end up, you're always doubling the volume, so you're always going to be halving the concentration, okay? So equal volumes are mixed means double the volume, therefore half the concentration. All right, so the concentration of silt, where'd you go? What happened? Where'd it go? Oh my God. What number was it? 82? Okay. Just went away. Okay, that was exciting. All right. So we have concentration of silver is equal to the concentration of AgNO3 diluted, which is 2 times 10 to the negative 2 molar times 1 over 2 is 1 times 10 to the negative 2 molar. Concentration of bromate is equal to the concentration of sodium bromate diluted. So that's going to be 3.6 times 10 to the negative 3 molar times 1 over 2 is 36 divided by 2 is 18. So that's 1.8 times 10 to the minus 3 molar. So our precipitate then is AgBrO3 in equilibrium with Ag plus and BrO3 minus. And so KSP is just silver times bromate. Thank you very much. And that's going to be 1 times 10 to the negative 2 times 1.8 times 10 to the negative 3, which is, 1.8 times 10 to the negative 5. And then we have to look and we have to say silver bromate. Ooh, I'm going to say trial KSP here because I wrote KSP instead of Q. Whoopsie. Okay. And so KSP for AgBrO3, we would need to go look that up. Silver bromate, 5.3 times 10 to the negative 5. What did I do before? Oh, I'm confused now. It's okay, we'll sort it out. (5.3 times 10 to the negative 5). That's so weird. I swear I did this question before and got something different. However, that would mean that our answer would be B. Was that what it was originally? Okay, so the answer is B. Oh, what's wrong with me? Yeah, should be B. Answer should be B. Let's go change that one back. 82. Answer is B. Maybe I was reading the wrong question or something. 78, okay. Okay. KSP is equal to x squared, because it's a one-to-one compound. And so x is equal to the square root of 1 times 10 to the negative 12, which is 1e12 negative square root is 1 times 10 to the negative 6. And then the molar mass of cadmium carbonate is cadmium 112.4, 112.4 plus 12 plus 16 times 3 is, so that's moles per liter, times 172.4 grams per mole, 1.7 times 10 to the negative 4. So it should be D. What did I say it was? You don't know. Let's go look. D, 78 is D. Yeah. Yeah. Okay. Anything else? No? Yes? 61. All right. In which of the following would solid silver chloride be the most soluble? Well, I can tell you right now that this has a common ion, common ion, common ion. So it would be lower solubility in this one, lower in this one, and lower in this one because it's in they have the ion in common, and so it would be the most soluble in NH4NO3. But if we want to look at it a little more closely, we can say we have AgCl in equilibrium with Ag plus and Cl minus. If I add HCl, I'm increasing chloride, shifting to the left. That makes it less soluble. Same thing if MgCl2 would increase the chloride, shift it to the left. That would make it less soluble. Silver nitrate, that would be increasing the silver ion, which would shift it to the left, which would make it less soluble. And NH4NO3 does nothing. Those are both spectator ions. They don't react with anything. So doing nothing is going to be more soluble than any of the others, which actually make it less soluble. Yes? 35. What do you remember about concentration? Concentration is independent of volume. So we can ignore the 2 liters. It is irrelevant. And we have 1 mg Mg2 plus, 2 Br minus. If this is 0.25 molar, then this is 0.25 molar, and this is twice that, so that's 0.50 molar. So that would be C. How we doing? Yeah, there will be 14 marks. So in the neighborhood of 4 to 6 problems. Somewhere between 4 and 6. It'll be 14 marks. 22 multiple choice, 4 written response questions. Or 5, or 6. 14 marks. ¿Algo más? No? You guys can't kill another 5 minutes for us? Because, like, honest to God, like, we only got... You don't want any written response? You were happy with all the written response? Yes. 18 written. If a solution of calcium nitrate is added to a saturated solution of calcium sulfate, a precipitate is observed to form. Explain why this occurs, including any relevant equations, and identify the precipitate. Okay, so we have a saturated solution of calcium sulfate. So I would say relevant equation, solubility equilibrium equation for calcium sulfate, CaSO4, solid in equilibrium with Ca2 plus SO4 2 minus. Now, to that we add calcium nitrate. What do you know about nitrate salts? Soluble. So calcium nitrate, one-way arrow or two-way arrow? One-way arrow because it is soluble. Ca2 plus 2NO3 minus. I'll start you off. When CaNO3 is added to the CaSO4 solution, what happens? Not yet. What does it do? We just wrote what it did. What does it do? It releases calcium ions into solution. And therefore what? The concentration of calcium does what? Increases. Okay. Where should we go next? No, not shift, because we need to say this will cause and I'm going to call this 1, and I'm going to call this 2. This causes equation 2 to do what? To shift left why? To use up Ca2 plus to bring concentration Ca2 plus back down. Therefore, less CaSO4 is dissolved. Therefore, solubility has decreased. is good? Alrighty, you successfully staved off learning anything new today? We'll see how the other block does. They never seem to have any questions.